Okay, let's get started. So far in this chapter dealing with electrochemistry, what we have been looking at are reactions, which are redox reactions, that produce energy in the form of electrical energy, all right? So basically, the reactions are spontaneous reactions, and as such, they are, in most cases, exothermic, but in any case, they will provide electrical energy. And the electrical energy will, of course, be manifested as a flow of electrons through an external circuit. What we'll be looking at here, pretty much for the rest of this chapter, is basically kind of like the opposite or the reverse of what I just described. In that, in these cases, we'll be looking at using an electric current to drive a reaction that would be otherwise non-spontaneous, all right? So an example of that would be, and by the way, this term here, electrolysis, is basically what I'm talking about. Basically using an energy, electrical energy to drive a non-spontaneous reaction. So here's an example of that. The electrolysis of sodium chloride. Now, over here represents a apparatus that is used to carry out this electrolysis of molten sodium chloride. So what does that mean? Molten means basically that the sodium chloride is melted, so therefore it's now in a liquid state. So that term molten is usually applied to high melting point solids in a liquid state, all right? So what we have here, we have an anode, a carbon anode, which is an inert electrode, and we have an iron cathode here and here. And basically what we said earlier with respect to the galvanic cells is that at the cathode, reduction always takes place, and at the anode, oxidation takes place. And that is no less true in the case of the electrolysis of any particular ionic compound. So the oxidation reaction that would take place at the anode, oh, by the way, so as I said before, the sodium chloride is molten over here, right? Over here is basically the same thing. We have molten sodium chloride. So in the molten state, in the liquid state, you're going to have ions floating around freely, right? So therefore, what will happen is that you're going to have the chloride ions floating around and the sodium ions floating around. The sodium ions will be attracted to the cathode, while the chloride ions will be attracted to the anode, right? Because after all, the anode is positively charged and the cathode is negatively charged. So what's going to happen at the anode, as I said before, is oxidation, where the chloride ion will undergo oxidation to form chlorine gas, all right? And the electrons that are produced will enter the external circuit. So as you can see in this diagram here, you see at the anode bubbles emerging, that's a chlorine gas emerging, right? In the case of the sodium ions, they will be attracted to the cathode, as I said before, and they will undergo reduction because the electrons in the external circuit now will enter the cathode and will combine with the sodium ions to form sodium in the molten state, in a liquid state. So as you can see here, the sodium is being led out through these pipes here and here, all right? And that's what happens in the case of the electrolysis of molten sodium chloride. So that's basically what electrolysis is all about, right? Because sodium chloride will not spontaneously decompose on its own, right? Sodium chloride, if you get a piece of sodium chloride and sit it here, it stays there forever, right? In order for it to decompose, energy must be expended. And in this particular case, the energy is in the form of electrical energy, all right? And here's another example, the electrolysis of water. Now, in this case, we have water here, but what they have done in order to facilitate the solution being very susceptible to conduction is that they add a small amount of sulfuric acid. So it's a dilute sulfuric acid solution, right? But what will actually happen in this particular electrolysis process is that water will be electrolyzed, right? So there are two reactions that will be taking place. You have the oxidation reaction taking place again at the anode, where water undergoes oxidation to form hydrogen ions and electrons, and oxygen as well. And then in the case of the cathode, reduction will take place. Now, because this solution is dilute sulfuric acid, you're going to have a relatively high amount of H plus ions present, so that will undergo reduction to form H2, all right? So basically, that's the reaction that will take place. And if you were to add these two equations together, in fact, let me see if I can squeeze that somewhere here. But what I'm going to do is, I'm going to write down the reduction reaction down here. So that would be 4H plus 4 electrons to form 2H2. So of course, the hydrogen ions, so the hydrogen ions will cancel out. What's going on with this here? The hydrogen ions will cancel out here and here, and the electrons will cancel out here and here. And what you'll be left with when you add them up, I'm going to write it down here, is 2H2O liquid to form 2H2 plus O2. All right. So the overall reaction that will take place is the formation of hydrogen and oxygen, right? Again, by itself, this would not be a spontaneous reaction, right? If you get some water and sit it here, it will stay there forever. No reaction will take place. No decomposition will take place, right? So again, this is another example of using an electric current to drive an otherwise non-spontaneous reaction. This time, the reaction is a decomposition of water to form hydrogen and oxygen. And this picture here, this photograph here, basically shows you the setup that is used to carry out this reaction. And you'll notice in the test tube where hydrogen and oxygen are collected, there's a 2-to-1 ratio between the hydrogen and oxygen. And that reflects the 2-to-1 ratio between the hydrogen and oxygen in the balance equation here, all right? So that's basically what happens in the electrolysis of water. So using those two examples, we can clearly see that electrolysis can be used to drive certain non-spontaneous reactions, all right? Okay, now what we're going to look at is some more quantitative aspects of electrolysis, right? We can actually determine, based on the amount of current and the time under which the current has passed through the water or the solution or whatever we're trying to electrolyze. We can, based on that, determine ultimately how much product you expect to get, all right? So this is a flow chart which basically helps you to do that. Basically the current and the time, when you multiply those two, that gives you the charge, right? Current multiplied by time gives you the charge. If you haven't done any physics, then this should look familiar to you, right? And then we convert, so that is charge in coulombs, and then we convert to Faradays. Remember we said that 1 mole of electrons will carry a charge of 96,500 coulombs. That's Faraday's constant, right? So basically we can convert from coulombs and divide by the Faraday constant to determine the moles of electrons. And then based on the mole ratio between the number of electrons or the moles of electrons and the moles of the substance to be oxidized or reduced, we can determine the mass, the moles of the substance previously, and then we can determine, based on the molar mass or the ideal gas equation, of course, it depends on what the question is asking for. We can determine the mass in grams, or we can determine the volume, or we can determine the pressure if you're given the volume. So it depends on how the question is posed, all right? So let's look at this particular example to demonstrate how we can take such a quantitative approach. This question is asking how much calcium will be produced in an electrolytic cell of molten calcium chloride if a current of 0.452 amperes is passed through the cell for 1.5 hours, right? So there are two reactions or half reactions that we'll be concerned with. Actually, there's only one half reaction that we'll be concerned with. The anode reaction is not that important, even though it's going to occur, and that's the anode reaction, the oxidation of the chloride to form chlorine, right? But the important reaction that we need to be aware of is the reaction that is taking place at the cathode, I'm sorry. And the reason why that's important is because the question is asking how much calcium will be produced. And it is at the cathode where the calcium will be produced as a result of the reduction of the calcium ions. So that's a reaction right there. And it's very important that the equation is balanced, because what will be important is the mole ratio between the number of electrons and the calcium, right? That's the important aspect of this equation that you're going to use, excuse me, to answer this question. So when you add these two equations together, of course, you're going to get the net reaction. Again, this is a non-spontaneous reaction, and the only reason why it will occur is because we are using an electric current to drive this reaction, right? Now, so as I said before, this is the important relationship between the moles of electrons and the moles of calcium, which is given by the second half equation, right? So basically, how do we get the moles of calcium? We're going to start off with the current, which is, as I said before, 0.452 amperes. Now, the ampere unit, I think I mentioned this before, is the same thing as coulombs per second, all right? So what we're going to do now is, based on the current that has flowed through the cell, we're going to convert this to coulombs. So what we have to do is multiply by the time. Now the time would be 1.5 hours, but because we have seconds here, what we need to do is convert that to seconds. So that's why we need to multiply by 3,600 seconds per hour. And then we multiply by the mole ratio, or I should say the ratio between the moles of electrons and Faraday's constant, all right? So that will give us the moles of electrons. And then because of the 1 to 2 mole ratio between the calcium and the moles of electrons, we multiply by this to get the moles of calcium, right? So the hour units will cancel out here and here. The second units will cancel out here and here. The coulomb units will cancel out here and here. And the moles of electron units will cancel out there and there. So the only unit remaining will be the moles of calcium unit. So you do your number crunching on your calculator, and when you have completed that, you're going to end up with the moles of calcium being produced being 0.0126 moles. But the question is asking, and that's it, pretty much. I thought the question was asking for the grams, but you don't need to do any further. Once you get the moles, that's basically it. Of course, if the question is asking for the mass in grams, then of course you know what to do. You'd have to multiply the moles of calcium by the molar mass of calcium, and that will give you the mass in grams, which in this case is 0.50 grams. All right, so that's basically how that is done. All right, any questions about this particular example? Any questions? Yes, sir.
What do you multiply to the moles to get grams of calcium?
You have to multiply by the molar mass. So that means that you have to multiply this by, you have to multiply this by 40.08 grams of calcium over 1 mole of calcium. And that will give you the mass in grams of calcium. All right? Okay. Any other questions about this? Any other questions? All right. So this is pretty much the end of the chapter. This is just an example of what we have learned in this chapter, how it applies to certain situations, such as the corrosion of dental filling. Something that I've experienced myself, because when I was in Jamaica before I just got up here, I had to see my dentist, and because I was experiencing some pain, a toothache, and it turns out to be a decay. And he filled it with mercury amalgam, which is basically an alloy of mercury and tin, right? So that's basically what he did there. And then after I came up here, I started feeling some pain there again, and then the filling actually fell out. And it turned out that basically some redox reactions were taking place where the tin part of the mercury, the tin amalgam actually underwent some oxidation, so therefore there was some corrosion. As a result, the size of the filling became a bit smaller, and therefore it fell out. So, well, that tooth has been removed since then, so I don't have any issues with that anymore. But this is just one example of how, what we have learned would apply to this particular situation. And these are basically the potential values for the different types of reductions that are taking place when it comes to these reactions, all right? Okay, and that's basically it for this chapter. So, based on what we have just done, and let me just say this. So, if you remember, I said that there's an addendum to assignment 7, which I published. I've made some modifications to it, and I've republished the new assignment number 7 with the modifications. So, what I'm going to give you guys now is the most recent edition, so to speak. which deals with what we're just talking about just now. And for you guys out there in Zoom, I'm going to, if I've not done so already, publish the new version of assignment number. Okay, so that's not what I want. See here. Assignments number 7. I think this is it. Oh, no. Assignment number 7, and then no, that's what I'm looking for. Wrong one. Okay, where is it? This is it. Did I publish? Okay, so it's published. All right, so let's look at this together. All right, so let's look at the first question. It says, in an electrolytic cell, the negative electrode is negative because it has, what do you think the answer is? Is it too many or too few electrons? Too many, exactly. So too many would be the answer here. Okay. Okay, chemicals that come into contact with the negative electrode will be, or will, what? Gain or lose electrons? Gain electrons. And B, is it oxidized or reduced? Reduced. And the electrode in electrolysis is called what? Cathode or anode? Cathode. All right. So the next question is, write the change that water goes through at the cathode. So therefore it's water. We saw that equation earlier. It's water plus electrons to form OH minus and H2. So to balance this, we're going to need a 2 here and a, hold on. We're going to need a 2 here, 2 here, 2 here, and 2 electrons here. 4, 4, 2 oxygens, 2 oxygens, 2 negative charges. Okay, so this would be the reaction, the half reaction that water will undergo at the cathode. All right. Okay, so any questions so far? Any questions? Any questions? Okay, let me clear this because I need to scroll down to the questions below. Okay, now number 3 now is asking, in an electrochemical cell, the plus electrode is positive because what? It has too few electrons. Too few. All right? Chemicals that come into contact with the plus electrode will lose electrons and be oxidized. And then it says the plus electrode in the electrolysis is called the anode, exactly. Right? Okay, So the question in number 4 is asking, write the change that water undergoes at the plus electrode. Now, this one, we did not see in the PowerPoint, so let me just write it out for you. It's going to be H2O to form H plus O2, all right? Plus electrons. So to balance this, we're going to need a 2 here. Actually, we're going to need a 2 here. We're going to need a 4 here. And here we're going to need 4 electrons. All right? So that would be the reaction that would take place at the anode when water is oxidized, right? So these are 2 reactions that you need to remember. The one for the oxidation of water and the one for the reduction of water, right? Okay. In fact, number 5 is asking for you to add these 2 equations together and make sure the electrons cancel out. So the first reaction we had was H2O plus electrons to form OH minus plus H2. And to balance this again, we need 2 here and 2 here and 2 here. And for this one now, it's 2 H2O to form 4H plus O2 plus 4 electrons, right? So the question is asking for us now to add these 2 equations together. In order for us to do that, we have to make sure that the number of electrons gained and lost are the same. So what does that mean?
Multiply the top one
I
by
have to multiply the top one by 2, right? So this would be equal to 4 water molecules plus 4 electrons to give 4 OH minus plus OH minus plus H2. So we're going to add that to this here. Let me just write this one below here. 2 H2O. I'm sorry?
Isn't that 2 H2?
2 H2. Yeah, you're right. Not here. Here, you're right. Okay, so for the second equation, it's 2 H2O to give 4H plus O2 plus 4 electrons, right? So the 4 electrons will cancel out here and here. Anything else will cancel out? Okay, so we're going to end up with, now there's one thing I should mention here. These water molecules on the same side would add up. So you're going to end up with 6 H2O. And then on the product side, these 4 hydroxide ions will add to 4 H plus ions to get 4 H2O. And then you're going to have plus 2 H2 plus O2, right? And then you should recognize that these 4 water molecules will cancel 4 of these, leaving behind 2. So basically, you're going to end up with your final answer, let me write it up here, would be 2 H2O to give 2 H2 plus O2. So this would be the final answer when you add those 2 equations to each other. All right? Okay, any questions about this? Any questions? Any questions? No questions? All right, let me clear this and continue scrolling below. Now for this one, and I should have done this earlier, for this one, we're going to need that table. And that table, let me see if I can bring this on the screen, would be the table of standard EMF values. So tables, standard reduction potentials. Okay, so this is what we're going to need. All right, so let me go back to the, not that one. This one, okay. So the question says, we will perform the electrolysis of an aqueous solution of sodium sulfate. Both sodium ions and water molecules will be attracted to the cathode. Which chemical is more likely to be reduced, all right? Now, in order for us to answer that question, scroll up, we have to look at the possible reduction reaction that would take place at the cathode, right? Now, one of them would be the reduction of sodium, which would be Na plus electrons to give Na, right? The other reaction, Na, the other reaction is a reduction of water, which we saw before, H2O plus electrons, 2 electrons to form OH minus, 2OH minus plus H2, and we need a 2 here, right? So in order for us to predict which one is more likely to occur, we have to look up the EMF values for their reduction in each case. So that's why we need a table. So the first thing I'm going to look for in the table is the reduction of sodium ions, its EMF value. Where is it? Where is it? Sodium. Okay, where are you? Okay, sodium, minus 2.71. So the EMF value in the case of sodium is minus 2.71 volts, all right? And then in the case of the reduction of water, see if I can find that. Okay, it's right here. The reduction of water, the value here is minus 0.83 volts. Minus 0.83 volts, all right? Okay, so now that we have those two values, then the question now becomes, which of these two is higher? Because the one with the higher EMF value is the one that's most likely to occur at the cathode, all right? So which one is most likely to occur? The water, the reduction of the water. So the answer here you're going to put would be the water. The water is more likely to be reduced because its reduction will have a higher EMF value. All right? Okay. Any questions about that? Any questions? Questions? Okay. So scrolling down now to number 7. Let me clear this here. So scrolling down to number 7, same thing, but this time we're talking about what happens at the anode. This time, it's the sulfate and the water that will be attracted to the anode. And the question again is, which one would be more, or which is going to be oxidized? So now we're going to look at oxidation, which is the reverse of reduction. So we already met what will happen in the case of water. Water will undergo oxidation to form H plus O2 plus electrons. And to balance this, we need a 2 here, a 4 here, and a 4 here, right? Now, in this case, we have to be careful when we're looking for what will happen in terms of the EMF value, because remember, the table gives you the standard reduction potential. So what we're going to look for is the equation where this is reversed in the table, right? So we're looking for water, H plus and oxygen plus electrons to form water, which is right here, right? So the value here is 1.23 volts. So let me write that down here. So the EMF of this will be, now this is 1.23 volts for the reduction, which means for the reverse, which is what we have here, would be minus 1.23 volts, right? So please note that for the reaction here, that is plus 1.23 volts. But what we're interested in is the reverse reaction, right? So therefore, the EMF value will be the opposite, or the sign will change from plus to minus, all right? Now, the other reaction that we'll be concerned with is the oxidation of the sulfate. So let me write this down here. Right, now, I'll be honest with you, I don't know what the result of the oxidation of the sulfate is. So basically, I'm going to go back to the table and look up a situation where sulfate is the product of a reduction. So let me see where that would be. Unfortunately, when you're doing problems like these, again, you have to take some time to look in the tables and see. Okay, so here it is. The sulfate is the product. So when sulfate is oxidized, it forms this, which I think is called a perasulfate ion plus 2 electrons, right? So basically, the EMF of the reverse reaction would be minus 2.05, right? So what I'm going to do here is write down for the oxidation of the sulfate ion, the formation of S2O8, 2 minus, plus 2 electrons. And the EMF of that would be equal to minus 2.05 volts, right? So now that we have those two values, we can now answer the question, which was, which chemical will be oxidized? And again, we go to looking at which one has the higher EMF value, right? Or reduction potential, right? So between these two, which one is higher? Exactly. So water will undergo oxidation at the anode, right? So again, the question is asking for you to write the reactions at the electrode, at each electrode. So for the cathode, it was H2O plus electrons to form OH minus and H2. And to balance this again, we need a 2 here, a 2 here, and a 2 here. And at the cathode, at the anode, I'm sorry, it's going to be 2H2O to give 4H plus O2 plus 4 electrons. And again, the answer will be the same as what we saw earlier. Multiply that by 2, and we add these together, and you're going to get the final answer being 2H2O to form 2H2 plus O2. And that would be how that is done. All right? Any questions about this one? Any questions?
Cathode, was it taken for the last problem, or
I'm sorry?
was the cathode taken?
Yeah, it's the same reaction, the same reduction reaction, where water is reduced to form hydrogen and hydroxide ions. Okay, any other questions about this one? Any other questions?
So when we do, when the question says oxidized, which chemical will be oxidized? Does that mean we're looking for the reverse?
Exactly, because all the values that are given in the table, go back to the table here. All the values that are given in the table are all reduction half reactions and their EMF. So when it comes to looking for the reaction, which is an oxidation reaction that will take place in the anode, you have to look for the reverse in the table, and then for that half reaction, you're going to change the sign. So if the sign was positive, you're going to put negative, and vice versa.
And then if it's looking for which chemical will be more likely to be reduced.
Then you just use the straight from the table, whatever the equation is, because these are all reduction half reactions.
For the form of it with less electrons.
I'm sorry?
You're looking for the form of it that would have.
Where the electrons would be on the left side of the equation.
Yeah.
Right, exactly. All right. Okay, any other questions? Any other questions? Okay, so if you understood what we just did for this one, let's see. Okay, what am I doing here? Okay, so let me clear this. And let's scroll down. Okay, so in this case now we're looking at electrolysis of potassium iodide, right? So the potassium ion and the water will go to the electrode, the negative electrode, which is the cathode. So the question is, which is more likely to be reduced? So again, you'd have to go to the tables, right? So what would you look for in the case of potassium? Turn this on. what would be the equation you'll be looking for the reduction of potassium,
Electron,
right? To give?
K.
Okay, so we would have to look for the EMF value for that half reaction. So let's see if we can find it here. Potassium, where are you? Where are you? Okay, here it is, minus 2.93. All right, so the EMF value for potassium is minus 2.93 volts, all right? And then now we do the same thing for the reduction of water. So the reduction of water equation is the same as the one that we saw before, which is H2O, come on, which is H2O plus electrons to form OH minus plus H2. And again, we need 2 here, we need 2 here, and we have 2 electrons here. And the standard EMF value, I don't want to look for it again. Can somebody remind me what the value is? We did it before. The reduction of water EMF value.
Negative 0.83.
1.83? Okay.
Negative 0.83.
Yeah.
0.
I'm sorry?
0.83.
Oh, 0.83. Okay. Volts. Okay. So again, we compare these two. Which one is higher? The water. So the water is the one that's going to be reduced. Let me see here. So they didn't ask for which is more like, but we know what's going to be oxidized. All right. So the water is going to be oxidized. So basically the answer for number 9 is the same as the answer for number 8, right? Because the cathode reaction would be the same reaction, right? And the anode reaction is the same reaction, which is 4H2O to give 4H plus 2O2 plus 4 electrons. And you do the same thing, multiply the first one by 2 and then add them up, and you're going to get 2H2O to give 2H2 plus O2. And that's it. All right? So the result would be the same in the case of the electrolysis of potassium. Oh, wait a minute. Hold on. Oh, okay, I jumped the gun a bit. I shouldn't have put this here. Oh, okay. All right, tell you what. I mistakenly put this here, so I'm just going to eliminate it. So let me scratch this out. I'm sorry about that, right? Because I didn't do the iodide part yet, right? So scratch that part out, all right? You're still going to put water here, right? But scratch this part out. And then now we're going to look at number 10, where it's asking for what will happen as far as the iodide and water being attracted to the anode is concerned. So let me clear this. And again, we have to look at the oxidation reaction that would take place. Now, in the case of the iodide, when that undergoes oxidation, it's going to form I2 plus 2 electrons, right? And in the case of water, it's the same as before. Let me do it here. H2O oxidized to form 4H plus 2O2 plus 4 electrons, right? So now we have to look at the EMF values for these half reactions, right? So again, we have to go to the tables. So where is the table? And we're going to look for the oxidation. Well, we're going to look for the reduction of I2, because that's the reverse of the oxidation of I minus. So here it is right here. You don't have to go far to find it. the reduction of I2, the EMF values of that is 0.54. So for the oxidation, is going to be the reverse, which is minus 0.54 volts. And then now for the oxidation of water, we did that before, so can you help me out again? Because I don't want to spend time searching for it. What was the EMF value for the oxidation of water? Minus 1.23 volts, right? So in this case, let me rewrite it here. This is, is it minus 0.54? Minus 0.54? Okay, so in this case, we're comparing minus 0.54 volts to minus 1.23 volts. So which one is higher? Exactly. So basically, it's the iodide that would preferentially undergo oxidation at the anode, right? So in this case, the cathode reaction is what I said before, which is the reduction of water to form OH minus plus H2. We need two here, we need two here. But in the case of the anode, this is the reaction that would take place. So that would be 2I minus to form I2 plus 2 electrons, all right? Gonna need 2 electrons here, right? So when we add these two, what will be the result? The electrons will cancel out, so you'll be left with what? 2H2O plus 2I minus to give 2OH minus plus H2 plus I2. And that would be the overall equation for that particular electrolytic cell. All right? Any questions about that? Any questions? Any questions? Yes, ma'am.
So, the iodine was the anode because it had a greater EMF value. Is that why?
Right.
Okay.
That reaction is more likely to occur than the oxidation of water because it has a higher EMF value. Remember, the EMF value or the reduction potential or whatever you want to call it is a measure of the tendency of a particular reaction occurring. So the higher that value, the more likely that would go, especially when you have two species going to the same electrode. The one with the higher EMF value is the one that's more likely to occur at that electrode. All right?
And also, so for number 7,
Number 7.
we did the cathode and the anode was both water. So how come it was like, why were they both water for them?
Well, water is one of the species that would potentially undergo a change, oxidation or reduction, depending on the electrode. So you have to consider that. You have to consider the oxidation of water at the anode, and you have to consider the reduction of water at the cathode, right? But the other species will come into play. So like, for example, in the case of the sulfate and water, right? You have to look at, okay, what would be the value of the EMF when water is oxidized? And what would be the EMF of the reaction when the sulfate is oxidized? And then you compare those two EMF values. The one that's higher is the one that's more likely to occur. And that's basically what it comes out. All right? Okay, so let me clear this. And scroll down. So we just did number 10. Okay, let's look at 11. So in the case of 11, it says in the electrolysis of copper 2 sulfate, both the copper 2 plus and water will be near the electrode. So let's look at what happens as far as the reduction of copper 2 plus and water. So Cu2 plus 2 electrons is the reduction of the copper 2. And as far as the water is concerned, again, this would give you I'm sorry, this should be 2. This should give 2OH minus plus H2. Oh, so this should be okay. I think this is it. All right. So what was the value again for the reduction of water?
-0.83.
Okay, and now we have to look up the value for the reduction of the copper 2 plus. So we have to go to the tables. Okay, copper 2 plus, copper 2 plus plus 2 electrons. The value for that is 0.34 volts. So okay, so that's 0.34 volts, that's minus 0.83 volts. So which one is more likely to occur at the cathode? Which of these two reduction reactions? Exactly. So you're going to have Cu reduced at the cathode. And then as far as the sulfate and water is concerned, we did that already. So this is just basically repeating what we saw earlier. And if I remember correctly, it's a water that will undergo oxidation, right? So let me put H2O here. So now we need to write down the cathode reaction, which is Cu2 plus 2 electrons, and the anode reaction, which is H2O oxidized to form 2H plus, actually 4H plus O2 plus not to do that, and then plus 4 electrons, and then the overall reaction, we have to multiply this by 2 so that the 2 electrons or the 4 electrons will cancel out here and here. So the final answer would be 2 Cu2 plus 2 H2O to give 4 H plus O2 plus Cu and 2 Cu, and that would be it. All right. Any questions about this one? Any questions? All right. Continuing. Let me clear this. Scroll down. Okay, now question number 12 says that silver plating occurs when the electrolysis of silver sulfate solution is used because the silver metal is formed at the what? Where will the silver be formed when you electrolyze silver? Would it be formed at the cathode or the anode?
The cathode?
The cathode. So we're going to put cathode here. And it says this is the
Negative.
okay. The reaction at the cathode will be Ag plus electrons to give Ag, right? Okay, so that's relatively simple. The next question is a more quantitative one. It says, let me clear this. It says that recall that 1 ampere second is the same thing as 1 coulomb, which we talked about earlier. And Faraday's constant is 9 to 6,500 coulombs, which is the charge carried by 1 mole of electrons. So the question says, if a cell is run for 200 seconds with a current of 0.250 amperes, how many grams of silver solid will be deposited? So the first thing I would do is write down the equation for the formation of silver as a result of the reduction of silver ions. So that would be the equation. That's important because we need the mole ratio between the electrons and the silver, right? So the next step is I would determine the charge carried by the 0.250 amperes of current running for 200 seconds, right? So that would be 0.250, and amperes is the same thing as coulombs per second, and I will multiply that by the time, which is 200 seconds, and that gives you the amount of charge. Now, what we need to do is find out the mole equivalent of that charge, and the way we do that is that we multiply by 1 mole of electrons above and the amount of coulomb below, which is Faraday's constant, which is 96500 coulombs, right? So this will cancel out with that. This will cancel out with that. So the only unit remaining would be the moles of electrons, which we have to convert to moles of silver. Because it's a 1-to-1 mole ratio between those two, then we multiply here by 1 mole of silver divided by 1 mole of electrons. So that cancels out with that. So you're going to end up with moles of silver, but we're not finished yet because the question is asking for the mass in grams of silver, right? So we need one more conversion factor, which is the molar mass of silver. So we're going to have 1 mole of silver down here, and the mass in grams of silver above. Can you tell me what the molar mass of silver is, please, from the periodic table over there?
7.9.
107.9 grams of silver. Okay, and that's it. So let me work this out. So that would be 0.250 times 200 divided by 96500, and then multiplied by 107.9. And according to my calculations, this works out to be, when rounded out to 3 sig figs, 0.0559 grams of silver. And that's how that is done. All right? Any questions about this one? Any questions? No questions? Any questions out there in Zoom? Okay, clear this and scroll down. I think this is the last question. Okay, so this question says, a current of 10.0 amperes flows for 2 hours through a cell containing a molten salt of metal X. This results in the decomposition of 0.250 moles of metal X at the cathode. So the question is asking, what is the oxidation state of X in the compound? In other words, what's the charge carried by X, right? So we don't know what the charge is. That's what we're trying to find out. So the first thing I would do is write down an equation for the reduction of X in the ionic form. And the way I would represent that, I would say let N be the charge, right? So Xn plus N electrons will give you X. That would be the equation I'll be working with, right? So the aim is to find X. Okay, so how do we find X? Let me see. What I would do is I would find out how many. Okay, I'll start off with the 10.0 amperes, which is the same thing as coulombs per second. And then I would try to find out how many coulombs have passed through. That means we have to multiply the time in seconds, right? They gave us the time in hours. So we have to do some conversion here. So I would multiply this by 2.00 hours, multiply by 3,600 seconds over 1 hour, right? So the seconds will cancel out here and here. The hours will cancel out here and here. So you'll be left with coulombs. The next step is I would multiply this by 1 mole of electrons divided by 96500 coulombs. That's the charge carried by 1 mole of electrons. So the coulombs will cancel out here and here. So now we're going to get the moles of electrons resulting from that calculation. So let's see what that gives. 10 times 2 times 3,600 divided by 96500. And according to my calculation, this works out to be equal to 0.746 moles of electrons, right? Now, the question continues to say that the moles of the metal would be 0.250 moles, right? Now, based on this equation here, the ratio of the moles of the X to the moles of N would be 1, or let me do the other way around. The moles of the electrons divided by moles of X would be equal to N over 1 based on this equation. And that would be equal to the moles of electrons here, which is 0.746 moles, divided by the moles of the metal X, which is 0.250 moles, right? So 0.746 divided by 0.250 gives 2.98. But since we know that the number should be an integer, we can simply round this off to 3. So what does that mean? That means that the charge on the metal X will be +3. And that's basically how that is done. All right? Any questions about this particular example? Any questions? Any questions? Okay, so that's it for this chapter. So what you're going to do is, when you're submitting this, you're going to basically submit that along with the assignment number 7. So assignment number 7 plus the addendum will be submitted. In fact, what I'm going to do now is set up a Dropbox for that. So let me clear this. And let me do this. And that. And then assignment. And this is assignment number 7. And let me see. Today is the 29th. Okay, so I'm going to let this be due on the 31st. So let me go here. Okay, so available from today until the 31st. All right, so assignment number 7 and the addendum together should be submitted in that Dropbox. All right. Okay, so let me move on now to the next chapter, which is the nuclear chemistry chapter. All right. And this will be the last chapter for this course. So we're almost there, right? Okay, nuclear chemistry. Now, in order for us to delve into this particular topic, we have to remind ourselves of some terms that you would have learned in General Chemistry 1, or better yet, high school or introductory chemistry, right? Atomic number, we all know what that is, right? By definition, the atomic number is the number of protons in the nucleus of an atom, all right? And then the other term that you should be familiar with is the mass number, which is the sum of the number of protons and neutrons present in the nucleus of an atom. And what you're going to see is that in this chapter, what we'll be concerned with are changes in the nucleus. That's what nuclear reactions are. Nuclear reactions are reactions that occur in the nucleus of the atom. They are different from chemical reactions because in the case of chemical reactions, the changes that takes place are not in the nucleus, but in the amount of electrons around the nucleus, especially the valence electrons, right? So that's a main difference at the microscopic level between a nuclear change or nuclear reaction and a chemical reaction, all right? So that's why we're concerned with these two terms. So of course, you should be familiar with this representation, the symbol. In some textbooks, they call it the isotopic symbol, where the A, which is written as a superscript, is the mass number, and the Z, which is written as a subscript, is the atomic number, right? So that's the element symbol. A is the mass number, Z is the atomic number, right? So if you see something like this, like 3216 sulfur, right? This tells you a lot of stuff, right? It tells you the atomic number, which is the number of protons. It tells you the mass number, which is the sum of the protons and neutrons. And therefore, based on those two, you can determine the number of neutrons. And of course, it tells you the element as well, right? Now, there are some other symbols which you're going to encounter from time to time in this chapter. This symbol represents a proton. You can use this or this, doesn't matter, right? That's a proton, okay? Then, and again, you notice that it's written in the same format as here. So that means that the atomic number is 1 and the mass number is 1 in the case of a proton. Then we have what is known as a neutron. Now, the neutron is a particle which, as the term suggests, is neutral. It has no charge, right? So what nuclear scientists, people who are responsible for the nomenclature and the symbolism and all that, what they have decided to do is that to use this as a symbol for the neutron, where the atomic number for the neutron is said to be 0, and the mass number would be 1, right? So that's basically the neutron. And then we have the electron, where the charge is -1. So basically, the atomic number is said to be -1, and the mass number is 0. Even though the electron does have a mass, but the mass number, based on the definitions, according to nuclear scientists, that is just said to be 0. And I should add that you can use this symbol here or this symbol, right? And the reason why this symbol can be used is because in the context of nuclear reactions where electrons are involved, these particles are called beta particles, right? So we use the symbol beta here, and we can use this symbol to represent electrons involved in a nuclear reaction, or we can use this. It doesn't matter which one you choose to use, all right? Okay, and then there's another particle known as a positron, which is seen as the opposite of the electron, right? And you can use this symbolism or this symbolism, right? And then there's another one. Oh, and by the way, the mass number is 0 for the positron, just like in the case of the electron, and the atomic number is +1. And then we have what is known as the alpha particle, which is the helium-4 nucleus, right? So basically, it's a helium-4 nucleus where the mass number is 4 and the atomic number is 2. And again, you can use this symbol or this symbol. Again, it doesn't matter which one you want to use. Anyone is fine according to the rules, all right? So these are some fundamental particles that will be involved in a lot of the nuclear reactions that we will encounter in this chapter, all right? So let's talk about how do we write and balance nuclear equations. And you're going to see some significant differences between balancing nuclear equations as opposed to balancing chemical equations, right? The first thing you need to recognize when it comes to balancing nuclear equations is that you need to conserve the mass number. What does that mean? It means that the total mass numbers on the left side of the equation must be equal to the total mass number on the right side of the equation, all right? And I think so this is basically what I just said. The sum of the number of protons and neutrons must be equal as far as the reactants and products are concerned, right? So here's an example of this, right? If you bombard uranium-235, which is what this is, with neutrons, then this is the reaction that would take place, right? And if you look at this equation carefully, if you look at the mass number, if you look at the total mass numbers on the left side, that's 235 for the uranium plus 1 for the neutron. So that's equal to 236, right? And if you do the same thing on the right side, where you add the 138 for the cesium plus 96 for the rubidium plus 2 times 1 for the 2 neutrons, you're going to get that also being equal to 236, all right? So that's one thing you need to ensure whenever you're writing down or whenever you're balancing a nuclear equation. You need to make sure that the sum of the mass numbers on the left side will be equal to the sum of the mass numbers on the right side, all right? The next thing you need to make sure is that the atomic numbers are conserved as well. In other words, the sum of the atomic numbers on the left side of the equation is equal to those on the right. So going back to the same equation right here, right, you're going to see that as far as the atomic numbers on the left side is concerned, it's 92 plus 0. So the total atomic numbers would be 92. And on the right side, when you add 55 to 37 to 0, 2 times 0, that's also 92. So therefore, the atomic numbers are conserved, right? So those two things have to be conserved when it comes to balancing nuclear equations. The total number of mass numbers on the left side must be equal to those on the right, and the same is true for the atomic numbers, all right? Okay, so with that said, let's see how we can use this to solve problems such as the one that I have here on the screen. So this question says, polonium-212 decays by alpha emission. Write the balanced nuclear equation for the decay of polonium-212, right? Now, you'll notice that they did not give the atomic numbers here. However, no problem, because each element has their own unique atomic number, right? So all you have to do in order to determine the atomic number of polonium is consult the periodic table, right? So if you consult the periodic table, you see that polonium has an atomic number of 84. Now, the question says that polonium decays by alpha emission. So what that means is that when polonium decays, alpha particle is produced and another nucleus would be produced, right? So the key thing here is to figure out what the other nuclide is. And that's very easy because of what we just said in the previous slide. Basically, we have to make sure that the mass numbers and the atomic numbers will be conserved. And by so doing, you can determine the mass number and the atomic number of X, right? So if we look at the mass numbers on the left side is 212, and the mass number total on the right side is 4 plus A. So we can set up an equation like this. And all we have to do is solve for A. So therefore, A will be equal to 208, right? And then we do the same thing for the atomic numbers. We have 84 here, which must be equal to 2 plus Z. So we set up that equation, and then we solve for Z, which would be equal to 82, right? So we know that the nucleus here that is produced is one that has an atomic number of 208, a mass number of 208 and atomic number of 82. So again, we go to the periodic table and look up the element that has the atomic number of 82 so that we can identify what X is. And it turns out that X would be equal to lead. So therefore, this now would be the balanced equation for this nuclear reaction. And that's basically how this is done. All right? Any questions about this example? Any questions? Any questions? All right. So let me talk about comparing nuclear reactions to chemical reactions. And you're going to see some significant differences. I think I mentioned one before, which is that there are changes in the nucleus, right? Which is number 2, the point number 2 here when you compare the two. But let me start from number 1. In the case of chemical reactions, as we all know, you have bond breaking, bond making, rearrangement, atoms coming apart and then coming back together again to form new products, right? In the case of nuclear reactions, what actually happens in most cases are elements being converted from one to another. Or if there's no change in the element itself, there will be a change to an isotope of that element, right? So that's one important difference between nuclear reactions and chemical reactions. The other difference is that in the case of chemical reactions, there'll be changes in the number of electrons in the molecular or atomic orbitals. In the case of nuclear reactions, there'll be changes in the number of protons, neutrons, and electrons and other elementary particles. In the case of chemical reactions, the amount of energy changes that takes place in a chemical reaction is relatively small compared to what happens in nuclear reactions, right? So if you compare nuclear reactions to chemical reactions, let's say you're looking at the same amount of reactants, the nuclear reactions will generate or absorb a lot more energy compared to in the case of chemical reactions. And then the fourth difference between these two is that the rate of a chemical reaction can be affected by several factors: temperature, pressure, concentration, and catalysts. In the case of nuclear reactions, their reaction rates will not be changed by any of these factors, right? So it doesn't matter if you change the temperature or change the pressure or whatever, the rate will still be the same, all right? So those are basically the 4 differences between chemical and nuclear reactions, all right? Okay, so let me start you off with the final assignment, assignment number 8. Go. Okay, so, and for those of you out there in Zoom, I don't remember if I published this, so let me do that now. I've done this before. Assignments, number 8. So I did not publish it. Okay, so. All right, so, okay, so basically these are all equations, nuclear equations. And the question says, circle the missing particle in the following nuclear equation. So basically you need to find out which of these would be the correct answer for filling in this blank right here. So they gave you what's happening on the left side, and you're to figure out what will be the product, all right? So if you remember what we just said, we said that basically in any balanced nuclear equation, the mass numbers must be conserved and the atomic numbers must be conserved, right? So the total mass numbers on the left must be equal to that on the right, and the same is true for the atomic numbers, right? So in the case of the first one, we're gonna look at the mass numbers first, right? So we have 214, we have 2 times 4, circle it like this, and then we have 2 times 0. So what's that total? So that's 214 plus 8. So that's 222. So whatever the product is, the mass number would be 222, right? And then we do the same thing for the atomic numbers. So that's 84 plus 2 times 2. So that's 4. So that's 86. Or 88, I'm sorry, 88. So whatever the product is here, it's 88, right? So then, oops, come on. This thing just 88, all right? So the question now is, what is the identity of the element? So we have to go to the periodic table, and I can't see it from here. So which element has an atomic number of 88? Can somebody tell me? Which element has an atomic number of 88?
Radium.
Radium, which is Ra, right? Is it radium or radon?
Radium.
Rn?
Ra.
Okay, so radon, right? So that means that the answer is D. All right? And that's basically what you're going to do for the others in that first couple of questions. Any questions about this? Yes, sir.
Or
Hmm?
negative.
Oh, my bad. Oh, I'm sorry. My bad, my bad. I made one error. You know what the error I made is? Can somebody tell me? This is not right. What's the error I made? It should be 86. Why should it be 86? Exactly. Thank you. So that's a mistake I made. So this should be 86, which means that the answer is what I just circled. Yeah. All right. Okay. Any questions about this? Okay. So let me see if you can do a couple of the others. Let me here it is. So let's see here. So how would you do number 2? What would go here?
Europe.
Okay,
Minus 1 on bottom.
exactly. So which one of these would it be? Exactly. Okay. What about number 3? Well, on the right side, we have, for the mass numbers, we have 142, 91, and 3 times 1, right? So let me see what that gives. 142 plus 91 plus 3. So the mass number total on this side is 236. But we have 1 here, right? So what would be the mass number of the element here?
So
235, all right? And then now, as far as the atomic numbers are concerned, on the right side, we have 56, 36, and 0. So 5, 6 plus 3, 6, according to my calculation, that's 92. So the next step is to identify the element with the atomic number, 92, and that element is what? Uranium, U. So that means that A would be the answer for that one. All right? Any questions about that? Okay, let me clear this. Scroll down. Okay, so number 4. What's the answer? Let me hear what you guys have to say about this one.
Should be C,
Should be C? Okay, why do you say that?
because the atomic number,
Okay, so this is 13 and 2, so that's 15. So you have 15 here, so whatever it is here, that should be 0, right? And then the top part, the mass numbers, 27 and 4, that's what? 31, which means that over here you should have 1. So therefore, the only species that fits that would be the neutron. Okay, number 5. Now, number 5 is a bit different because in this case, you need to find out how many neutrons that you're going to end up. So you need a coefficient right here. So again, you add up the total on the left side, which is 235 plus 1, so that's 236. And then on this side, you have 139 plus 95, and that's 234, right? So what number would go here as a coefficient? Exactly, right? And then just to make sure, if we add 53 to 39, that gives you 92, which balances with the 92 here. So the number 2 would go right there, right? Okay. I'm sorry? Here?
yeah.
No, it will be 2 because 139 plus 95 gives 234. Oh, wait a minute.
Plus 1 would be 235.
then you have 2, because you multiply it by 2.
Would be 1 times 1.
Right, so this would be 235, right, on this side, and here is 235 plus 1. That's 236. So you're going to need 2 of these here. All right, so the answer is actually 2. Okay. Any questions about this one? Any questions? All right, let me clear this. Then scroll down, see what happens. All right, I'm going to leave you to do the rest. Based on what we have done before, I think you should be able to do these. And if you have any questions, of course, please come and see me about that. So there's a whole lot of them for you to get some good practice of, right? 20 questions in total of that type, right? All right, so let me go back to the PowerPoint. And let's talk about different types of nuclear decay. And how can we tell whether or not a particular nucleus will decay? In other words, is there any way of making any predictions as to whether or not a particular nucleus will be stable? So, oh shoot, what did I do? Okay, so let's look at what happens when beta decay occurs. So beta particle, as we said before, is the same thing as an electron, right? So if we look at, for example, carbon-14 undergoing beta decay, this is the reaction that would take place, right? You're going to end up with your beta particle, and then the resulting product would be nitrogen-14, right? And this symbol here basically represents radiation being emitted. We're going to say more about that when it comes to nuclear reactions. In some cases, radiation would be emitted. In other cases, radiation would be absorbed. All right. Here's another example. Potassium-40, when it undergoes beta decay, it forms calcium-40. All right. So what is actually happening in the nucleus when this happens? Well, what actually happens in each case is that a neutron in the nucleus is converted to a proton and a beta particle, right? So the neutron is converted to a proton and a beta particle. The proton remains in the nucleus and the beta particle is emitted from the nucleus in addition to the energy that's produced. As a result of that, the number of neutrons will decrease by 1. And there's also going to be an increase in the number of protons by 1 as well, all right? So basically, the neutron is converted to a proton, so therefore, there will be a reduction in the number of neutrons by 1, and there will be an increase in the number of the number of protons by 1, all right? So that's what happens in the case of a beta decay. Now, in the case of a positron decay, it's basically the reverse of what we just said here, because the positron is positively charged, right? So if we look at this, for example, the positron decay of carbon-11, right, to form boron-11, then, and another example here, where potassium-38 by positron decay is converted to argon-38, what happens is that the proton is converted to a neutron and a positron being formed, right? So basically what will happen is that the number of neutrons will increase by 1 and the number of protons will decrease by 1. That's because the proton is being converted to a neutron. And of course, the proton will remain in the nucleus and the neutron will be emitted. The neutron will be remaining in the nucleus and the positron will be emitted along with the radiation, all right? So that's what happens in the case of positron decay, right? In both cases, the radiation would have no mass number or atomic number associated. So that will not affect the other numbers that would be involved in both types of decay, all right? Then we get to electron capture, right? So electron capture is just basically what it sounds like, where the nucleus captures an electron and it forms a product. So in the case of argon-37, when it captures an electron, it forms chlorine-37, and radiation is also produced. And here's another example where iron-55, when it captures an electron, converts to manganese-55. And what happens in each of these cases is that when an electron is captured, it combines with a proton to form a neutron. And the neutron basically sits and resides in the resulting nucleus of the product, right? So what happens in these cases is that the number of neutrons will increase by 1 and the number of protons will decrease by 1, all right? And then we get to the alpha decay. Now remember, the alpha particle is a helium-4 nucleus. So we saw an example of this in one of the questions that we did earlier, where the polonium-212 undergoes alpha decay to form lead-208. And here's another example. Oh, I thought there was another example lined up. But basically the change that takes place in this case is that the mass number is decreased by 4, which means that the atomic number is decreased, or the number of neutrons is decreased by 2, and the number of protons is also decreased by 2, all right? And then in some cases, you might have what is called spontaneous fission. What is happening in these cases is that you have a larger nucleus undergoing a breakdown into smaller fragments, right? So this is what happens in the case of californium-252. When it undergoes spontaneous fission, it forms 2 particles of indium-125 plus 2 neutrons, all right? Now, so basically, we can have situations where the nuclei will just spontaneously undergo a breakdown, a fission, or undergoes a reaction with some other particle. So this begs the question, can we make some prediction as to which nuclei will undergo spontaneous decay? And how do we determine that? So people have been looking at that, and what they did was that they did a plot, right? What they did is a plot on this graph of the number of neutrons versus the number of protons, right? Now, this line that you see here is where the number of neutrons and protons is equal to each other, right? And what they did was to look at the different nuclei and see whether or not they will fall on this line. And what they found out was that the different nuclei that will undergo spontaneous changes actually falls within this belt of stability that's shown here. So basically what we're saying here is that when it comes to the smaller nuclei, they fall on that straight line, but as the nuclei becomes heavier and heavier, then basically the region in which they will lie will be above that belt of stability. Basically what they're saying is that for the larger nuclei, what you'll find is that the number of neutrons compared to the number of protons would be greater, well, the number of neutrons will be greater than the number of protons for the heavier elements to be less stable, right? So basically, when they become more stable by some decay, then the resulting product will fall closer to this belt of stability here, right? And if the number of protons, if the number of neutrons to protons is too large, if it is too small, then basically they will carry out some sort of decay in order to achieve a product which would fall within this belt of stability, right? So these are basically some things that were observed in terms of which nuclei would be stable. It turns out that certain number of neutrons and protons are extra stable. If the number of protons or neutrons is 2, 8, 20, 50, 82, and 126, or if the number of, well, that's it, as far as the number of neutrons are concerned. And it's kind of similar to what we observe when it comes to electrons in noble gases, where the number of electrons are these numbers right here, all right? Another thing that seems to contribute to the stability of nuclei is that nuclei with even numbers of both protons and neutrons tend to be more stable than those with odd numbers of neutrons and protons. And then basically this one says that all isotopes of elements with atomic numbers greater than 83, they tend to also be active or radioactive as well, all right? So this table basically summarizes, which type of isotopes will not undergo decay. In other words, they would be stable. All right. This last one here, all isotopes of TC and PM. I don't even know what those elements are. Those are radioactive. Okay. Now, we can quantitatively see whether or not a particular nucleus is going to be stable or not stable by looking at what is known as the binding energy. Let me just check something here quickly. Okay, so let's talk about what we mean by this term binding energy. The binding energy is basically the energy to totally break up a nucleus into its constituent particles, protons and neutrons, all right? And what we're talking about here, for example, in the case of fluorine, is breaking up fluorine into its protons and neutrons. So fluorine has an atomic number of 9 and a mass number of 19. So therefore it has 9 protons and 10 neutrons, right? So the energy to break up that fluorine nucleus into the 10 neutrons and the 9 protons, the energy required for that is the binding energy. So that is represented by this equation right here. The binding energy plus this gives you the particles, right? The individual particles, right? Now, how do we calculate the binding energy? The key thing you need to realize when it comes to the binding energy is that, and this might sound a bit counterintuitive, it turns out that the total mass of the protons and neutrons present in the nucleus is not equal to the mass of the nucleus, right? The total mass of the protons and neutrons in the nucleus is not equal to the mass of the nucleus, right? That might sound weird, but that's actually the case, right? It turned out that there's a difference between those masses, right? And that difference between those masses, we call that the mass defect. Do I have it here? Okay, so delta M here, we call that the mass defect. Delta M is equal to the mass defect, right? The mass defect is what you get when you add up the masses of all the protons and neutrons, and then you subtract from that the mass of the nucleus. There's going to be a difference, and that difference is called the mass defect. And that mass defect is due to the binding energy, right? So the binding energy is related to, and in fact is proportional to, the mass defect, right? And this is the formula that we would use to calculate the binding energy. Delta M times c squared, the mass defect times c, which is the speed of light, squared, right? So whatever the mass defect is, you multiply by c squared, and that gives you the binding energy, right? So in the case of fluorine, we take 9 times the mass of the protons plus 10 times the mass of the neutrons, add them up and subtract from that the mass of the fluorine nucleus, and that will give you the mass defect. So you'd have to be given these numbers, right? You'd have to be given the mass of the proton, the mass of the neutron, and the mass of the fluorine nucleus, and plug them into this equation. And they would have to be, well, it doesn't matter what the units are for the masses, but usually the units are expressed in AMU, right? So when we work that out, this is what we get, right? The binding energy would be, or the mass defect would be the 0.1587 AMU. And then what you'd have to do now is convert this to kilograms and then multiply by c squared, which is in meters per second, to get the binding energy. So the way you do that is you take the 0.1587 AMU, and then you multiply that by a conversion factor, which allows you to convert from AMU to kilogram. And I don't remember what that is, but I know I gave it to you guys in a table. So let me look that up. So files. Remember, it's something like 1.66 times 10 to the minus 27. Let me fundamental constant. Oh, here it is, 1.6. I was right. Okay. That's what I should know myself. So it's 1.66 times 10 to the minus 27. Um, 1.66 times 10 to the minus 27 kilograms would be equal to 1 AMU, all right? So you're going to convert from AMU to kilograms, and then you're going to multiply this by the speed of light, which is 3.00 times 10 to the 8 meters per second squared. And when you work that out, you're going to get 0.1587 times 1.66 times 10 to the minus 27. And I forgot to put this within parentheses. Times 3 times 10 to the 8 squared. And according to my calculation, this works out to be equal to 2.371, actually 2.37 times 10 to the minus 11. You know what, let me do this again because I'm quite sure I made some mistake here. 0.1587 times 1.66 times 10 to the minus 27 times 3 times 10 to the 8 squared. Okay, so I guess I was right. So this would be, and the units here would be kilograms meter squared over second squared, which is the same thing as joules. So 2.37 times 10 to the minus 11 joules, all right? So that would be the binding energy. And the binding energy is a bit of a measure of the stability of the nucleus. All right, now, I kind of went through a longer route just to explain to you how we get from AMU to joules. But what you can do is you can use this relationship here. Now, I'm not sure if this relationship is in the packet that I have posted in Canvas, but you may want to memorize this. 1 AMU is equal to 1.49 times 10 to the minus 10 joules. And you can use that as a conversion factor to convert from AMU to joules. You should get the same result as we have here, all right? In fact, let me see here. So yes, the answer is 2.37 times 10 to the minus 11, all right? Now, any questions about this? Any questions? Any questions? Okay, now let me clear this here because the true measure of the stability of a nucleus is what is known as the binding energy per nucleon, right? Now, a nucleon is basically a particle that is present in a nucleus, right? So the nucleons, of course, will be the protons and neutrons, right? So if you want to find out the binding energy per nucleon, what you do is take the binding energy that you calculated here and divide it by the total number of nucleons, and that would be the binding energy per nucleon. So in this particular case, you divide the 2.37 times 10 to the minus 11 joules by the total number of nucleons, which in this case is 19, and that will give you the binding energy per nucleon. In fact, the missing unit here would be per nucleon. All right? So that number is the actual measure that we look at to predict how stable a particular nucleus is, right? And again, researchers have looked at these values for different nuclei, and this is a plot that they came up with when they plot the nuclear binding energy per nucleon versus the mass number. And what they found was that of all the nuclei that exist, iron 56 is the most stable nucleus when it comes to the binding energy per nucleon. All right? So that's basically how that is done. All right? So as we said before, the greater the binding energy per nucleon, the more stable the nucleus is. Right? The greater the binding energy per nucleon, the more stable the nucleus is. All right? Okay. So with that said, what time is it now? Oh, okay. Let's quickly look at, where's my copy? Oh, all right, let me. Some questions again from your assignment. Number 8. Okay, again, unfortunately, the questions are not in the order as presented in the topic. So what I'm going to do is scroll down to page 6 of your assignment. All right. So they gave you, to begin with, they gave you the mass of the proton, they gave you the mass of the neutron, and they gave you this, which is the relationship between AMU and mega electron volts. Mega electron volts is another unit of energy. All right. So you have the joule unit, you have kilojoules, then there is a mega electron volt. So they gave you the relationship between the AMU and mega electron volt, and that can be used to answer energy questions in each of these cases. So in question number 24, it says tritium is an isotope of hydrogen, and it gives you the symbol of tritium right here, and it gives you the mass of tritium, all right? So the question is, what is the mass defect of this isotope? So the mass defect, of course, is the total mass of the particles minus the mass of the nucleus itself. So the way I would go about solving this is write down the equation for breaking up the tritium, which is 3,1H, into its constituent particles, right? So based on the formula here for tritium, you can see that tritium has 1 proton and 2 neutrons. So when this breaks up, you're going to have 1 proton plus 2 neutrons, 2 times 0, 1 neutrons, all right? So what we're going to do is find the total mass of these two to find the mass defect. So delta M is equal to the mass of the proton, which is okay, so the mass of the proton, which is 1.007825 AMU, plus 2 times the mass of the neutron, which is 1.008665 AMU. All right. And then I'm going to subtract from that the mass of the tritium, which is given right here. So that's minus 3.0160490 AMU. So let's see what that gives. So I'm going to add within the parentheses 1.007825 plus 2 times 1.008665, and then I'm going to subtract from that 3.010, no, I'm sorry, 3.0160490. And what I got, and please correct me if I'm wrong, but I got 9.106 times 10 to the minus 3 AMU. So that's what I got when I find the mass defect. All right? Okay, the next question is, what is the binding energy of this isotope? So the binding energy can be calculated using this, or you could use the other method that I showed you earlier, but I'm going to use this since this is here. So basically what I'm going to do is convert from AMU to mega electron volts. So 9.106 times 10 to the minus 3 AMU, I'm going to multiply that by 1 AMU down here and 931 mega electron volts. And let's see what that gives. So according to, oh, wait a minute. Okay, is that right? Hold on. Okay. Please correct me if I'm wrong, but I got 8.478 mega electron volts. All right, that's what I got. All right. Any questions about this? Any questions? Okay, so let me clear this. And scroll down. Now this is asking for the binding energy per nucleon, right? So binding energy per nucleon is binding energy per nucleon is equal to, what was the binding energy before 8.4 what? 78 mega electron volts divided by the total number of particles in the nucleus, which is what? For fluorine. For fluorine 19. I just told you the answer. It's 19, right? The total number of protons and neutrons. So I'm going to put 19 nucleons here. And then we do the math. So 8.478 divided by 19 So the answer here is 0.4462 mega electron volts per nucleon. Yes, sir.
Where did you get 19?
Because there are 10 neutrons and 9 protons in fluorine. Oh, I'm sorry. My brain is back to fluorine. This is tritium, right? Yeah. So that should be 3, not 19. My bad. I'm thinking of a previous example. So this will be 3 nucleons. So I need to redo this. So 8.4728 divided by 3. So this is 2.8. 2.824. 2.824 mega electron volts per nucleon. And that's how that is done. Okay, we're going to stop here, but based on what we have done just now, you should be able to do question 25, 26. Okay, so yeah, 25 and 26. You should be able to do. All right, so try those on your own. If you have any issues again, please let me know. All right. And just by way of announcement, so today I'm going to definitely send you back your graded work. I just didn't have time to do it yesterday. For both assignments numbers 5 and 6. All right, because that's what your test next week will cover. All right. So,
Can you undo it?
and I'll post the answer keys as well. All right. Okay, so that's it, folks. I'll see you guys tomorrow. And for those of you out there in Zoom, I'm